Your cloud infrastructure wasn't designed for scale, it was designed for speed. The portal click felt fast, immediate, safe, but speed and safety aren't the same thing. Configuration drift now drives 97% of security incidents for organizations today. That isn't just 97% of infrastructure issues. It is 97% of the entire security landscape. This isn't a technical problem anymore. It's a governance crisis. Infrastructure as code didn't win because it's trendy or because engineers like version control. It won because it solved a fundamental problem. It moved the source of truth from a human's memory to a versioned file. That shift changed everything. The death of ClickOps, why manual deployments became a liability. The portal interface was built for transparency, not scale. Every click felt deliberate and traceable. But traces fade when humans are the only record. What typically happens is a security engineer opens the Azure portal at 11 p.m. to fix a performance issue. There is network latency in the East US region, so they add an exception to the network security group just for one subnet to test a theory. They tell themselves they'll remove it tomorrow. Tomorrow comes. The ticket gets reassigned. The issue resolves itself. The engineer moves on. 2 weeks later, a compliance audit asks a simple question. Why is this rule open? Nobody knows. The change wasn't logged anywhere except in the Azure activity log, which nobody reads unless something breaks. The IRC template doesn't reflect it. The architecture documentation doesn't mention it. It exists only in the running environment. This is the ClickOps reality. 90% of cloud deployments experience configuration changes after the initial setup by privileged users. 90%. Not the outliers, not the poorly governed organizations. This is the baseline expectation. These quick fixes accumulate into what governance teams call posture drift. The model behind ClickOps is simple. Assume humans remember what they changed, why they changed it, and when it happened. Assume they'll document it. Assume the documentation stays synchronized with the actual environment. That model is broken. In a small deployment with 5 resources and 2 environments, you might get away with it. Humans have decent working memory for small systems. But scale it to 100 resources, scale it to 5 environments, add 5 different teams making changes, add a compliance requirement that your infrastructure must match your documented baseline. Suddenly the model doesn't just fail, it collapses. The real cost emerges when you try to scale. A financial services company with 500 Azure resources across 10 regions can no longer rely on individual engineers to remember the configuration state. A health tech company with strict HIPAA requirements can't afford undocumented changes to encryption settings or access policies. A retail organization with seasonal scaling can't track which NSG rules are permanent, which are temporary, and which are just forgotten. This is where organizations hit the wall. They reach a point where the gap between documented architecture and actual deployment is too wide to bridge manually. When this happens, they have 2 choices. They can invest aggressively in governance infrastructure and automation, or they can accept a growing security risk. Most organizations choose the first path, not because they love automation, but because they have no choice. The portal click felt safe. But safety requires knowing what you've changed and why you changed it. Safety requires reproducibility. Safety requires the ability to audit, trace, and if necessary, reverse every modification. ClickOps provides none of these things. It provides speed. You can deploy a resource in 30 seconds. You can modify a policy in 10 seconds. The interface is intuitive. The feedback is immediate. But the cost of that speed becomes visible only when you try to operate at scale. When you need to know whether every resource is properly encrypted. When you need to prove that your access controls match your security policies. When a regulator asks if you are sure every database backup is encrypted with the right key. At that moment, the portal becomes a liability because the source of truth isn't the portal. The source of truth becomes fragmented across human memory, documentation that drifts, configuration files that aren't updated, and the actual state of the environment. This is where the industry realized something fundamental had to change. Human governance couldn't scale. Manual tracking couldn't keep up with cloud complexity. The assumption that speed and safety could coexist in a portal-based workflow was broken from the start. We just didn't realize it until it cost us. Configuration drift as a governance collapse. Drift isn't a technical glitch, it's not a bug, it's not a misconfiguration that one patch or one policy update will solve. If you treat it like a technical problem, you'll miss what's actually happening. You'll spend money on tools and miss the structural failure underneath. Because drift is a governance failure. It's a failure in how organizations think about infrastructure ownership. Here's the distinction. When a human makes a manual change in the Azure portal, that change doesn't exist anywhere except in the running environment. It bypasses your ISC pipeline. It bypasses your code review process. It bypasses your audit system designed for Git commits. Audit systems are built to catch changes that flow through your source control. Portal clicks, they're invisible to that infrastructure. One engineer, one change, one click, and now your actual infrastructure no longer matches your documented baseline. But it's not just one change, it's hundreds of them, across dozens of teams, over months and years. A network administrator opens a firewall rule to debug a connectivity issue. They plan to close it the next day. That day never comes. A security engineer exempts a resource from a policy during an incident response. The exemption is meant to be temporary. 6 months later, the resource still has the exemption. A platform team adds a storage account for temporary testing. Testing ends. The storage account remains, now containing production data. These aren't intentional sabotage. These are normal operations, emergency fixes, temporary workarounds, each one reasonable in the moment, each one invisible to governance systems designed to monitor code repositories. This is the accumulation problem. 1 change is manageable. 100 changes are visible if they're logged. 10,000 changes? The logging becomes noise. The drift becomes the default state. Then comes the audit question. What is your actual security posture right now? And the honest answer is we don't know. Because your documented baseline, the infrastructure you think you deployed, bears only a passing resemblance to what's actually running. Every resource has a history of tweaks. Every configuration has been modified by someone, somewhere, for a reason that made sense at the time. And now all of that is baked into your production environment with no record of why it's there. This is what I mean by drift shifting governance from documented policy to living control. Your documented policy is the Git repository. It says, deploy this network topology, apply this security baseline, enforce this access control. Your living control is the actual environment, and it says, yeah, we tried that, but we also added these 3 exceptions, and opened this security group wider, and disabled this logging because it was generating too much noise, and exempted this resource from that policy because the project was in a crisis. These 2 versions of truth cannot coexist for long. The October 2025 Azure front door outage is the clearest recent example. 1 configuration change, not malicious, probably made by someone trying to fix something or optimize something, but invalid. And that single change propagated across Microsoft's global infrastructure, causing a 9-hour outage that affected millions of customers. This wasn't a software bug. This wasn't a capacity issue. This was a person making a change to a configuration, and that change not being validated before it cascaded through the system. Now multiply that risk across your entire organization, across hundreds of resources, across dozens of teams, across multiple cloud environments, and you see why 55% of cloud breaches trace back to configuration drift or oversight. Not misconfiguration in the design phase, configuration drift. The slow creep of changes made in production, never captured in code, never validated against policy, accumulating until the environment is unrecognizable from its intended state. When governance teams look at this situation, they face an impossible question. How do you govern something you can't see? You can write policies, you can create approval processes, you can implement access controls, but if every engineer can open the portal and change anything with their user permissions, if those changes don't flow through your governance pipeline, then your policies are only guides, not rules. This is the structural failure, not technical, organizational. The governance model has to change, from assuming humans will remember, from hoping documentation stays synchronized, from believing that periodic audits will catch the drift before it becomes a liability. It has to shift to a model where the infrastructure source of truth is immutable, centralized, and automatically enforced. And that requires moving to code. The shift from imperative to declarative, a conceptual revolution. This is where the fundamental shift happens. Not in tools, not in process, but in how you think about infrastructure itself. For decades, infrastructure was built imperatively. The model was, do this, then do that, then do this other thing. Follow the steps, click the button, execute the script, run the command. Each action was an instruction, a verb, an imperative. This makes intuitive sense to humans. We're procedural creatures. We think in steps. Step 1, provision a virtual machine. Step 2, attach a storage account. Step 3, configure networking. Step 4, apply security rules, follow the checklist, check the box when done. Scripts work this way, PowerShell commands work this way, portal clicks are imperative actions. You're telling the system to do something, to move from state A to state B through a series of explicit steps. But here's the problem with imperative infrastructure. Every step depends on the previous step being correct. If step 2 assumes a specific state from step 1, and someone manually modifies that state outside the script, then step 2 might fail. Or it might succeed but produce an unexpected result. You have to know the history of all previous steps to understand what the current state is, and you have to do those steps every single time you want to recreate the infrastructure. Declarative infrastructure proposes something radically different. Instead of describing steps, you describe the outcome, and you say, here is what the final state should be. Make it so. You're not telling the system how to get there. You're describing where you want to end up, and you're letting the system figure out the path. This is a profound shift in thinking. It moves the burden of correctness from the human operator to the system itself. Here's why this matters. If I deploy your infrastructure using a declarative model, and then someone manually changes a network security group rule in the portal, I can redeploy using the exact same code. The system compares the desired state, what the code says should exist, with the current state, what's actually deployed. It detects the difference, and it corrects it. Run the same code twice. The first time, changes are applied. The second time, nothing changes, because the desired state already matches the current state. This property is called idempotency. It's a cornerstone of declarative infrastructure. Reproducibility flows from idempotency. If I can run the same code 100 times and get the same result, then I can recreate an entire infrastructure from a single code file. I don't need to remember the sequence of steps. I don't need to maintain a checklist. I don't need human memory. The code becomes the source of truth, not the last successful deployment, not the documentation that describes what should be deployed, the actual code that defines the desired state. This is why configuration drift becomes visible in a declarative model. Drift is the gap between desired state in code and actual state in the running environment. And detecting that gap is trivial when you have a declarative system. Compare the two. Any difference is drift. Fix it automatically. Done. Imperative infrastructure can't do this. Imperative is fundamentally about sequences. If you remove a step from a script, you haven't described what the environment should look like. You've just changed the procedure. The environment might be in 100 different states, depending on what was deployed before. Declarative separates intent from implementation. Intent is, I want a secure network with these 3 subnets and these access rules. Implementation is, run this code to make that happen. The system owns implementation. You own intent. But declaring intent requires a language, a way to express desired state in code. And that's where ARM templates entered the picture. Section 4. ARM templates. The necessary mistake. ARM templates were a breakthrough moment. They moved Azure from a clickable UI to something you could version, review, and deploy through automation. You could finally express infrastructure as text. You could put it in Git. You could treat a deployment like a code change instead of a series of manual operations. The format chosen was JSON, and the logic was sound. JSON is universal. Every system can read it. Every programming language has a parser for it. If you want maximum interoperability, JSON is the obvious choice. But here's the problem. JSON was designed for data interchange. It was designed to shuttle information between systems, structured data, nested objects, arrays. It's perfect for sending a customer record from one service to another or for APIs to communicate. But JSON was never designed for humans to express intent about complex systems. When ARM templates embedded a domain-specific language inside JSON, they created a hybrid. Functions, expressions, string concatenation, variable substitution, all of this was hidden inside JSON syntax. You had to think like a JSON parser while also understanding the custom functions Microsoft bolted on top. Take something simple, a 3-tier web application. You have the network topology, the compute layer, and the database layer. You need proper isolation, security groups, load balancing, and managed identities. Then you add storage accounts, key vaults for secrets, and monitoring infrastructure. In ARM JSON, that's hundreds of lines. Deeply nested objects, resources in an array. Each resource has a nested properties object with dozens of fields. Some fields reference other resources using string concatenation and a function called resource_id that builds the full Azure identifier based on the subscription, resource group, and name. The cognitive friction is immediate. You're not writing infrastructure, you're wrestling with syntax. Brackets, quotes, commas, escaped characters. The mental translation from what I want to build to the JSON that describes it consumes your working memory before you even think about architecture. And the error messages arrive at deployment time, not authoring time. You write a 300-line JSON file and submit it to Azure. The system reads it, parses it, validates it against the schema, and then tries to deploy. 30 seconds later, you get a message. Unexpected token on line 287. There's a comma in the wrong place, or a bracket isn't matched. And now you've lost 30 seconds. You find the error. You fix it. You resubmit, wait another 30 seconds, repeat. Teams working with ARM JSON report higher error rates than teams working with simpler formats. They report longer code review cycles because scanning a 100-line diff of JSON requires intense attention to syntax. They report steeper onboarding curves for new engineers. You're asking them to learn Azure's resource model while simultaneously learning the quirks of how that model maps to JSON structure. The model behind ARM templates is straightforward. JSON is universal, so let's use it for everything. That model worked. ARM templates deployed real infrastructure successfully for years, but it created a secondary problem, a hidden cost that only became visible at scale, the readability crisis. As environments grew more complex and teams maintained larger libraries of templates, the gap between human intent and JSON expression became a productivity bottleneck. The code was correct, the deployment succeeded, but the human cost of maintaining it kept growing. By 2020, Microsoft was hearing consistent feedback from organizations using ARM templates at scale. These weren't complaints about capability. ARM could do everything needed. The complaint was about friction. It was about the effort required to read, write, and modify the templates. This is the moment Microsoft made a strategic decision. The cognitive load crisis. Why ARM failed at scale. Cognitive load theory comes from research in how humans process information. There are 3 distinct types of mental effort involved in working with complex systems. Intrinsic load is the cognitive demand of the problem itself. Understanding Azure's resource model is intrinsically complex. There are hundreds of resource types with properties, dependencies, and constraints. Understanding how a managed identity grants permissions to a storage account is difficult work, and no format choice changes that. Germain load is the mental effort you invest in building useful mental models. You have to understand how landing zones organize subscriptions and how policy assignments cascade through management groups. Building those conceptual frameworks takes work, but it's productive work. It builds expertise. Extraneous load is the cognitive friction introduced by how you express that knowledge. The tool's design, the syntax, the mental translation required. ARM templates maximize extraneous load. The syntax noise, brackets, quotes, commas, and deeply nested objects, consumes working memory before your mind even engages with architecture. You're parsing JSON while simultaneously trying to understand what the code describes. Your brain is split between two tasks. Is this valid syntax? And do I understand what this infrastructure should do? When that split happens, neither task gets your full attention. A Bicep file describing the same infrastructure is 30 to 50% shorter, not because Bicep is a shorthand or because it's doing something clever with compression. It's shorter because it removes structural noise. It removes the syntax that doesn't carry meaning. When you write in Bicep, the intent is immediately clear. You define a storage account, the Microsoft service, and the current API version. These are the defining characteristics. In ARM JSON, that same resource lives in an array called resources. Its type is specified in a type field, and its properties are nested in a properties object. The API version is part of a differently structured string. You're not reading about the resource. You're decoding the structure that contains information about the resource. Code review becomes painful with ARM at scale. A diff showing 100 lines of JSON is exhausting to scan. You're looking for meaning-bearing changes while simultaneously parsing syntax. A network engineer reviewing an ARM template change might miss a security group modification buried in 30 lines of indentation. The same change in Bicep is 3 lines. The security group is explicitly named, the rules are readable, and the diff is obvious. New engineers onboarding to ARM templates face a dual learning curve. They need to understand Azure's resource model, and they need to understand JSON quirks specific to how ARM uses it, the nesting conventions, the function syntax, and the string concatenation for building resource IDs all add up. You're asking them to learn 2 languages at once. Microsoft's own engineering teams reported something striking when they began transitioning from RMJSON to Bicep internally. They said the shift revolutionized their deployment experience. Faster authoring, fewer errors, easier reviews. These weren't metrics pulled from a study. These were product teams living with the tools. These were teams that had spent years mastering RMJSON and understood its quirks inside and out. And when given Bicep, they said it felt revolutionary. That word, revolutionary, isn't about capability. ARM could do everything Bicep does. Revolutionary was about friction. It was about finally being able to express intent without the syntax tax. The enterprise signal was unambiguous. Teams were staying on ARM not because it was superior. They stayed because switching costs were high. Once you've built a library of ARM templates and your entire CI/CD pipeline is built around them, the cost of migration exceeds the benefit of a better tool. That's the organizational stickiness of infrastructure tooling. Strategic decisions made 10 years ago still constrain choices today. But the fact that teams stayed on ARM despite its friction, and the fact that every team switching to Bicep reported it as an improvement, said something clear. The problem wasn't whether ARM could deploy infrastructure. The problem was the human cost of maintaining it. And that cost grew with every deployment, with every code review, and with every new engineer forced into the steep onboarding curve. This is the moment Microsoft understood something fundamental. You can't build governance at scale if the underlying tool creates friction with every interaction. Bicep as the answer, designed for humans, compiled for machines. Bicep is a language built for one thing, Azure infrastructure. It isn't a replacement for ARM, and it isn't trying to compete with it. Think of it as a translation layer. You write your code in Bicep, the tool compiles it into standard ARM JSON, and then Azure deploys that JSON. Every single capability that ARM templates support is available in Bicep. Nothing gets lost in the translation process, but the actual experience of writing the code changes completely. The philosophy here is simple. Get the noise out of the way. Keywords make this work. You use resource to declare what you're building and param to set up your inputs. You use var for variables, module for reusable parts, and output for what the template sends back. These words match how you actually think about infrastructure. There are no nested objects or messy property arrays to deal with. You just make clear, direct statements. In the old model, you had to use string concatenation to link resources. To reference one thing from another in ARM.json, you had to build a massive resource ID. You'd manually glue together the subscription ID, the resource group, the type, and the name using complex functions. It worked, but you had to decode the string just to read it. In Bicep, you just write stg name. The stg part is the name you gave your storage account earlier in the file. You want the name property, so you just ask for it. The compiler handles all that messy translation to the full Azure reference in the background. You read the code and you immediately see how things are connected. You also get real-time feedback through strong typing. While you're working in Visual Studio Code, the language server checks your work as you go. You aren't waiting until the deployment starts to find out you made a typo. You aren't sending a 300-line file to the cloud just to have the parser fail on line 287. The errors show up while you're still writing. The extension knows every resource type and every property that Azure allows. It knows what's required and what's optional. When you start a new resource, autocomplete suggests the right properties. If you use a name that doesn't exist, the editor hits you with a red squiggle immediately. You see the error, you fix it, and you keep moving. Modules are a core part of the Bicep experience. Breaking your setup into smaller pieces isn't a workaround or an afterthought. In the old ARM model, nesting templates was a nightmare, but Bicep makes it the standard. You put your networking in one file and your virtual machines in another. Then, you call those files from your main template using the module keyword. You pass in your data and you grab the results. The intent is obvious. This is how you handle scale. If you need to deploy the same setup across 10 different regions, you don't copy the code 10 times. You take one module, tell it which region to use, and run it 10 times. Bicep makes this feel natural, while ARM makes it feel like a chore. The way companies are adopting this follows a very clear path. New projects on Azure are defaulting to Bicep. Teams starting from scratch choose it because it's easier. The old ARM setups stay where they are because moving them is expensive, but the new platforms are being built on Bicep. By 2026, about 20% of companies will use Bicep as their main standard. Another 30% will keep their ARM templates, and the rest will use tools like Terraform. The direction is clear. Bicep isn't winning because of a marketing push or because it's the latest trend. It's winning because it fixes the gap between how you think and how you have to talk to the machine. The adoption pattern, why legacy systems persist. Just because Bicep is better doesn't mean everyone switches overnight. This is where the technology hits the reality of how companies actually work. Large organizations don't swap out their infrastructure code the way they might upgrade a database. Usually big decisions come from the top. A budget is set, a plan is made, and the team moves the data. There's always some friction, but the company can usually handle the transition. Infrastructure tools are different because the cost of switching is massive. Take a large bank as an example. They might have 300 ARM templates running their entire Azure environment. These templates handle everything from the network to the disaster recovery plan. They've spent years tuning these files. Their deployment pipelines are built specifically for them. They have automated tests and audit logs all tied to ARM. The entire system is hardwired into that one format. Then someone walks in and says Bicep is better. The math just doesn't add up for them. If you have 300 templates and it takes 30 minutes to rewrite and test each one, that's 150 hours of work. But it's actually much worse than that. You have to run both systems at the same time during the move. Your documentation is split in two. Your team has to learn 2 languages. Your code reviews get twice as complicated. And what do you get for all that effort? The old system works. It's annoying to maintain, but it's a pain the team already understands. Bicep promises to make things easier in the future, but it doesn't give them a new capability today. In that situation, most companies stay exactly where they are. It isn't because they don't like the new tool, it's because the effort of moving outweighs the benefit of the better technology. This is why we see such a specific pattern. New projects use Bicep. When a team builds a new platform from nothing, they don't have any baggage. They don't have old templates to fix or old pipelines to change. They pick Bicep because it's the path of least resistance. But the teams managing the stuff that's already running, they stay on ARM. By 2026, the market will show this divide. 20% of organizations will have moved to Bicep for their new work. 30% will still be managing their old ARM templates. The rest will be on Terraform or other tools. Most companies will actually be in 2 or 3 of these groups at once. They'll have a new app in Bicep and their core network in ARM. The tools we use for infrastructure are incredibly sticky. A decision a company made back in 2015 is still affecting what they can do in 2026. They aren't using ARM because it's better. They're using it because the cost of leaving is too high. This isn't a flaw in Bicep. It's just how enterprise technology works. Once a system is installed, it has its own gravity. It pulls everything toward it and makes it hard to leave, even when something better comes along. If you want to understand how technology changes, you have to look past the features. You have to look at the legacy systems and the capacity a company has for change. The real story isn't about which tool is the best. It's about how the old models keep a grip on the new ones. Configuration drift as the governance epidemic. Configuration drift used to be an operational annoyance. Now, it's a systemic governance crisis. But calling it a crisis actually understates what's happening. An epidemic spreads. It isn't isolated or contained. It moves through a population with patterns you can predict. Organizations see drift the same way. It isn't just one engineer making one mistake. It's hundreds of small changes across dozens of teams. These changes accumulate invisibly until the organization realizes it's been infected. In Azure, drift touches everything. It hits resource configurations, platform services, and identity settings. You might find a single database with encryption modified through the portal. A policy assignment might be scoped differently than the documentation says. A managed identity might have broader permissions than anyone intended. You might even find a network security group with rules that nobody remembers adding. These aren't failures of individual engineers, they are symptoms of a broken system for controlling change. The primary driver is obvious. Manual portal changes. An engineer needs to debug a network issue at 2 a.m. They modify an NSG rule as a quick fix. They plan to revert it once they understand the problem. 3 weeks pass and the rule is still open. Nobody reverted it. Technically, it's still a temporary change. In reality, it's permanent. Emergency incident response follows the same pattern at high velocity. During a production outage, a team disables a policy constraint to unblock a deployment. They are right to do it because speed matters more than governance during an incident. But when things return to normal, that policy exemption lingers. It sits on a ticket somewhere to be re-enabled. That ticket gets deprioritized as other work comes up. The exemption becomes part of your infrastructure. The accumulation is exponential. 10 changes might be visible. 100 changes become noise that is impossible to audit manually. 1,000 changes become your baseline state. At that scale, organizations stop asking if they have drifted. They start asking how far the drift has gone. The discovery point is usually brutal. A compliance audit arrives. Your regulatory requirements state that infrastructure must match your documented architecture. An auditor compares your approved design against what is actually deployed. The gap is catastrophic. It isn't in any single resource, but in the aggregate. 50% of your network rules don't match the topology diagram. Access policies have exceptions that contradict your least privilege standard. Security groups have rules that open attack surfaces you didn't even know existed. The audit discovers the one thing you didn't want to know. Your actual infrastructure looks nothing like your intended infrastructure. What makes this an epidemic is the mechanism. The same drivers produce drift in every organization. The same blind spots hide it. The same discovery moment surfaces it. This pattern repeats across industries and cloud platforms, regardless of the organization's size. Regulatory response is shifting because of this pattern. National cyber agencies now explicitly require continuous monitoring and remediation of drift. They understand what organizations are learning the hard way. Static standards are meaningless if you can't enforce them every single day. HIPAA compliance doesn't matter if an encryption setting drifted off 3 months ago and nobody noticed. PCI DSS network isolation doesn't matter if an NSG rule was modified and forgotten. SOC2 controls don't matter if identity policy exemptions have accumulated beyond anyone's recollection. The governance model has to shift. We have to move away from static standards and documents that describe how things should be. We need continuous enforcement and real-time validation. We need automated remediation that catches drift the moment it happens, not months later during an audit. This shift isn't optional anymore. It is the price of operating cloud infrastructure at scale. The alternative is an organization where governance is theoretical and compliance is just an uncomfortable surprise waiting to be discovered. This is where the infrastructure as code model becomes non-negotiable. IAC as the governance control plane. Infrastructure as code is not just a faster way to deploy resources. That's what people think when they first encounter it. They see version control and CI/CD pipelines. They think it's about getting changes deployed quicker. That is true, but it isn't why the model won. IAC won because it is the only mechanism that makes governance possible at scale. Think about what governance actually is. It isn't a person or a committee. Governance is a system that translates policy intent into actual behavior. If a policy says all databases must be encrypted, governance is the mechanism that ensures it stays that way. It works today, it works tomorrow, and it works when a new engineer joins the team. It is the automation that makes policies stick. Without IAC, governance is just aspirational. You write a policy and hope people follow it. You audit quarterly and discover violations that you have to fix manually. You hope it doesn't happen again. This is governance as a gate. It's a checkpoint that slows down change in hopes of catching violations before they reach production. With ISC, governance becomes a property of the code itself. Azure policy can evaluate your code before deployment and reject changes that violate your security baseline. Drift detection can scan your environment continuously to surface any deviation from your declared state. Automated remediation can then correct those deviations without waiting for a human to act. This requires 3 distinct layers working together. Structural controls form the foundation. These are your landing zones and management groups. They aren't policies, they are architectural guardrails. They make certain configurations structurally impossible. If you set up management groups to reflect your business units, it becomes technically harder to create unsafe configurations. A storage account in the wrong subscription will hit a permission boundary. A resource group outside the approved landing zone simply cannot be created. The architecture itself enforces your intent. Policy as code is the active layer. Azure policy definitions codify what is allowed and what is forbidden. These are rules that run during and after deployment. A policy can mandate that all storage accounts have public access disabled. When someone tries to deploy a storage account with public access, the policy blocks it. If someone manually enables it later, detection catches it and flips it back. Operational enforcement closes the loop. This includes CI/CD gates that scan code before it ever goes live. It involves integration with code review tools that flag violations early. You need continuous scanning of the live environment and dashboards that surface drift. You need automated ticketing that routes violations to the right team. The system doesn't just enforce, It makes that enforcement visible and traceable. When infrastructure is code, the entire process transforms. Change management becomes a code review. You aren't waiting for an approval committee. You are submitting a pull request for your colleagues to check. They look for security implications and validate the change against policy. This is vastly faster than traditional change management, and every decision is logged in the Git history. Audit trails become your commit history. If you need to know who changed what, the answer is in the commits. Every merge includes a message, and every change is attributed to a person. Rollback isn't a complex recovery process anymore. It is a Git revert. You deploy the previous version and you are done. The governance model is direct. You declare your intent in code. You run it through your policy engine. You deploy via your pipeline. You monitor for drift and remediate violations automatically. This model only works if the underlying code is readable and maintainable. This is why Bicep matters so much. Governance at scale requires code that people can actually understand and review. Complex and verbose infrastructure code becomes invisible to governance. Nobody reads a massive ARM JSON diff to catch a security violation buried in nested properties. But a clear Bicep template is something teams can actually review. They understand it, which makes governance real. And that brings us to the future, because ISC is about to be reshaped by AI. The AI agent problem, why human-written code might disappear. We've built the foundation. ISC is the control plane. Bicep makes it readable. Governance becomes possible when infrastructure is code. The system works. But now comes the disruption. AI agents are generating infrastructure code from natural language descriptions. You describe what you want, and the agent synthesizes a complete template. Build a highly available Kubernetes cluster with private networking, managed identity integration, and monitoring becomes a Bicep file in seconds. It's not a skeleton. It's not a starting point that needs human completion. It is a functional deployable template. This is powerful. Speed like this changes what's possible. An engineer stops context switching between documentation and the portal and code editors. They describe intent, the agent generates the implementation, they review it, they deploy it. The friction collapses. But power without constraint introduces new problems. The research is unambiguous. LLMs fail to produce secure infrastructure code at rates exceeding 40% on real-world tasks. These aren't syntax failures. These aren't failures that native tooling catches. These are security failures. Gaps where the code is technically valid and fully deployable, but leaves the infrastructure exposed. The patterns are consistent. Permissive defaults, a storage account deployed with public access enabled when best practice is private. An IAM policy granting broad permissions when least privilege is required. A database without encryption enabled because the agent assumed default settings were sufficient. A security group with rules wide open to testing that never got tightened. These aren't random errors, they're systematic failures in how AI models reason about security constraints. The problem is deeper than just incompleteness. Validation tooling can't catch these failures. When you run a validation on AI-generated code, it passes. When you run a plan, it shows the proposed changes. Both operations check syntax. Both verify that the code is structurally sound. Neither checks whether the resulting infrastructure is secure. Validation confirms JSON validity. A plan shows you the desired state and compares it to the current state. But neither tool evaluates whether that desired state implements your security baseline, whether it meets compliance requirements, or whether it leaves attack surfaces exposed. The agent generated a storage account. The code is syntactically correct. The plan shows the resource will be created, the validation passes, and the resulting storage account allows public blob access because the agent's model didn't encode a strong bias toward private access by default. This is dangerous, not because humans are immune to mistakes. Humans make the same errors, but humans, if they understand what they're doing, apply judgment. An experienced infrastructure engineer reads a template and asks, why is this open? Should it be? An AI agent generates code following statistical patterns in training data, not through reasoning about your specific security requirements. The risk compounds as agents become more capable, as they write more code, as they handle more complex scenarios, and as they integrate deeper into your deployment pipeline. Humans become further removed from understanding what the code actually does. You trust the agent, you review the code, but your review looks for architecture and functionality, not for every hidden security gap. You deploy it, the template works, the infrastructure functions. Months later, a security scan flags the exposed access surface. This is where governance becomes absolutely critical. The assumption we've been building toward, that code is the source of truth, that policy can validate it, and that governance becomes possible. All of that depends on one thing. The human retains final authority over what gets deployed. The human understands the intent. The human owns the decision to accept generated code or reject it. AI agents must operate within policy guardrails, not autonomously, not with broad permissions, not trusted to make security decisions without oversight. They generate proposals. Policies validate those proposals. Humans review the validated output. CI/CD applies only what's been approved. This isn't pessimism about AI. It's clarity about what governance requires. The future isn't AI replacing humans. The future is AI generating intent, humans governing policy. The Guardrails model, how AI agents must be constrained. The gap between AI capability and governance control narrows when you apply a specific architectural pattern. Not a tool, not a band-aid, an operating model. The pattern is straightforward in theory. An agent generates infrastructure code. That code flows through validation. A human reviews it. Policy engines evaluate it against organizational constraints. If it passes all gates, CI/CD applies it. If it fails at any point, it stops. This creates a decision chain where automation amplifies human intent rather than replacing it. Policy as code is the critical enforcement layer. Azure Policy, Open Policy Agent, Sentinel, custom rules written in whatever language your organization prefers. These aren't aspirational guidelines. They're executable rules that run automatically. An agent proposes a storage account configuration. The policy engine evaluates it. The policy says, blob public access must be disabled. The proposed configuration has public access enabled. The policy rejects it. The agent's proposal never reaches the human reviewer. The system caught the violation automatically. This works because policies operate at machine speed. They don't require human attention. They don't slow down the workflow. They simply filter proposals before they reach the human decision point. An agent generates 500 potential configurations. Policy validation eliminates the 300 that violate your baseline. The human reviews the 200 that passed validation. Your review capacity is preserved while the agent's output is constrained. Agents can propose changes. Policies determine what's allowed. That's the division of responsibility. The agent doesn't need to understand your full security posture. The agent doesn't need to know every compliance requirement. The agent generates plausible infrastructure. Policies encode your constraints. The system enforces alignment without requiring the agent to be a governance expert. This design keeps the human in control while capturing the productivity gains from AI. You're not trusting the agent to make security decisions. You're using the agent for synthesis speed while policies protect against misconfigurations. You gain the benefit without the risk. Least privilege access for agents is non-negotiable. They should never hold broad permissions. They should never have long-lived credentials that persist across sessions. Every agent execution operates with specific scoped access for that specific task. An agent generating a storage account gets credentials that allow storage account creation in a specific subscription. Not broader cloud permissions, not permissions to modify access policies or networking rules, just enough access to do the specific thing you asked it to do. Every action the agent takes must be logged, traced, and auditable, not just the final code that gets deployed. The entire decision chain. Which tools the agent invoked, what parameters were passed, what validation rules were applied, what outputs each step produced, what the human reviewed, what decisions the human made. This creates visibility. If something goes wrong, you can trace back through the agent's reasoning and find where the failure occurred. Organizations are beginning to deploy what amounts to agent firewalls, model proxies that sit between the agent and your cloud environment. These proxies intercept tool calls. They verify that the agent is only using approved tools. They ensure that commands stay within the agent's assigned scope. They inject logging, they enforce rate limits, they can detect if an agent is behaving anomalously and shut it down before it causes damage. This is the emerging pattern. Isolation by default, permissions minimized, every action logged, policies enforced, human oversight preserved. The governance principle is elemental. Automation increases risk unless it increases control proportionally. When you automate a process, you amplify the impact of errors. One person making a mistake affects one deployment. An agent making a mistake at scale affects hundreds. The only way to accept that amplification is to build control proportional to the automation. More visibility, tighter constraints, faster detection, automatic remediation, where safe. This model transforms AI from a trust problem into a governance problem. You don't have to trust the agent, you have to design governance that makes trust irrelevant. The agent can't do harm because the system won't allow it. That's where the real safety comes from. The strategic choice, Bicep versus Terraform in an AI-native world. By 2026, the world of infrastructure as code has finally settled into a predictable rhythm. It isn't a winner-take-all fight. Instead, we see a clear split. Terraform owns multi-cloud. Bicep owns Azure native. These tools aren't actually competing for the same crown anymore because they occupy different strategic positions. The choice you make isn't about which syntax you like better. It's a business decision about what your organization is actually trying to manage. Terraform is the standard for enterprises with a real multi-cloud strategy. These are organizations running workloads across AWS, GCP, and Azure simultaneously. They need to manage third-party infrastructure like GitHub or Datadog alongside their cloud resources. When you're provisioning Kubernetes clusters on 3 different platforms or orchestrating services that don't fit into one ecosystem, Terraform is the only choice that makes sense. It gives you a single, unified layer for everything. You get one language, one workflow, and one set of controls across the entire map. That's incredibly valuable when your infrastructure spans different continents and different providers. Bicep is the choice for organizations that have gone all in on Azure. It isn't necessarily better at the technical level, but it offers something Terraform can't. Deep native integration. You get day zero support for every new Azure service. There is a direct line between the Azure portal, the CLI, and the Bicep language itself. When Azure drops a new feature, it's in Bicep immediately, while the Terraform provider usually has to play catch-up. That lag matters when you're building on the cutting edge. Bicep also fits perfectly into the Azure governance model. Your landing zones are built in Bicep, and your policy as code flows naturally through Azure policy. The choice is less about what the tools can do and more about where you are going. For Azure-only shops, Bicep offers operational simplicity. You aren't paying a multi-cloud tax. You don't have to maintain a provider model that tries to translate Azure concepts into a generic language. You're writing directly against the Azure resource model, and that simplicity pays off when you look at your governance. Your policy frameworks and your access controls align perfectly with the platform. There is no translation layer and no mismatch in how things work. For multi-cloud teams, the trade-off is different. You accept a little bit of friction in any single cloud so you can have consistency across all of them. The unified model is more important than being perfectly aligned with one provider. You aren't optimizing for Azure speed, you're optimizing for organizational consistency. Moving between these tools is expensive. Most enterprises don't actually switch. They just standardize on one tool for what they have and then make new decisions for new projects. If a company is running ARM templates and Terraform at the same time, they usually don't consolidate everything. They just decide that new cloud-native services go in Bicep while cross-cloud components go in Terraform. They would rather live with two tool chains than pay the massive cost of a full migration. The arrival of OpenTofu changed the math here too. It's a community-governed fork of Terraform that is fully open source. When HashiCorp changed the licensing for Terraform back in 2023, it made a lot of people nervous about vendor lock-in. They didn't want to be dependent on a proprietary license for their entire infrastructure. OpenTofu fixed that. It proved that the Terraform model could exist without being hostage to one company's business decisions. This made it much easier for organizations to commit to the model long-term. Hybrid strategies are now the standard for large companies. Terraform handles the foundation. It manages the networking, the shared services, and the cross-cloud pieces. Bicep handles the Azure-specific modules like compute and data services. This split actually makes sense for the people involved. Your platform team can use Terraform to manage the big picture across the enterprise. Your product teams, who only care about Azure, can use Bicep to move fast. Both teams get to speak their native language and move at their own pace. AI agents will generate code in whatever language you tell them to use. An agent doesn't care if it's writing Terraform or Bicep. It just produces valid code based on your standards. The underlying governance doesn't change. Policies still validate the work. Humans still approve the changes. The control plane still enforces what you intended to build. This strategic choice is vital because it sets your governance foundation for the next 5 years. The governance architecture shift from gates to operating models. For decades, we've treated governance like a gate. You build a service, it goes to a committee. They look at a checklist. They ask a bunch of questions. Then they either let you through or they stop you. This gate is designed to slow you down. The theory is that slow decisions lead to careful reviews, and careful reviews prevent expensive mistakes. In that world, the friction is seen as a feature, not a bug. But that model breaks when you try to scale. If you're managing 10 deployments, a committee is fine. If you're managing 100, it's a bottleneck. By the time you get to thousands of deployments across different business units, gate-based governance is impossible to manage. You would need so many committees that the whole company would stop moving. So what actually happens? The gate becomes a rubber stamp where people just click approve without looking. Or even worse, teams just bypass the gate entirely. They stop asking for permission and start asking for forgiveness, building workarounds that ignore the rules because the rules are too slow. The new model is different. It treats governance as an operating model that is baked into the work itself. It isn't a gate, it's an environment. It's a system of constraints that makes the right way the easy way. You don't wait for a checkpoint at the end. You weave the governance into every single step of the workflow. It's continuous, it's automated, and it's mostly invisible to the developer. They only see it when they break a policy, and that's when the system stops them and explains exactly why. This is a fundamental shift in what governance actually means. The old way assumes you can stop problems by being careful during an approval meeting. You're trying to catch mistakes before they hit production. The new way assumes that problems are going to happen, so it focuses on detection and correction instead. You make certain things structurally impossible, you make the right path easy, and you catch any deviations the second they happen. This new model needs 3 layers to work. First, you have structural controls. This isn't about policy, it's about architecture. It's how you set up your management groups and your subscriptions. If you design the hierarchy correctly, some violations can't even happen. A sensitive workload can't end up in the wrong spot because it won't have the right network connections. A database can't be put in the wrong region because the subscription doesn't have the quota for it. The architecture itself stops the mistake before anyone even tries to make it. Next is policy as code. This is the enforcement layer using tools like Azure Policy. These rules run automatically every time someone tries to deploy something. They are versioned, they are testable, and they are final. If an engineer tries to push a resource that breaks a rule, the deployment fails right then and there. It doesn't fail a week later during an audit. It fails the moment they hit submit. This turns policy from a boring document into a live system that people actually interact with. Finally, you have operational enforcement to close the loop. This means running scans in your CI/CD pipelines and using drift detection on your live infrastructure. If something changes and it shouldn't have, the system corrects it automatically or alerts the right team. The enforcement isn't waiting for a human to notice a problem. It's always running, always watching, and always checking for alignment. When you put these three layers together, the whole nature of governance changes. The governance team is no longer the department of numbered. They become architects. They design systems where compliance is the path of least resistance. They aren't checking every single change manually because they've built a platform where unsafe changes fail fast and safe ones move through smoothly. This requires a deep understanding of both the tech and the people. You have to ask why people are looking for exceptions in the first place. What is the business reason that makes someone want to break a policy? Once you know that, you can reshape the environment so the business goal and the policy goal are pointing in the same direction. This is where we see a new role appear. The power architect. Some people call it a governance architect. Their job is to design how decisions are made. They map out authority and build the control structures. It isn't a purely technical job, but it isn't purely organizational either. It's the bridge between the two. They understand that most transformations fail because the power structures never changed. They look at who has the authority to say yes, who needs to be consulted, and how conflicts get resolved. If you don't answer those questions, your governance will fail no matter how good your technology is. The power architect, a new role for a new model. The power architect is not your typical infrastructure person. They aren't the ones drawing network diagrams or picking out which Azure SKUs to buy. They answer a different question. Who actually gets to make the decisions? Who has the authority to pick those SKUs? Who can override a network change? And who do those people answer to when things go wrong? This role sits right at the intersection of teams that usually don't talk. IT operations, security, compliance, finance. In most organizations, these groups work in silos. But the power architect knows that a decision in one area ripples through all the others. When security locks down a network, developer speed drops. When finance cuts costs, the system becomes less resilient. When a business unit demands faster access, the audit trail disappears. Nobody wins when you optimize one piece of the puzzle in isolation. The power architect designs the authority structure so these interests align instead of fighting each other. It starts with a simple question. Who decides what goes into production? I'm not talking about the technical steps, I'm talking about the authority. An architect can suggest a plan and an engineer can build it, but who makes the final call? Is it the app team, the platform team, a security committee? The answer changes depending on the topic. A cost committee might decide on resource sizing, while security handles encryption standards. A risk committee might decide if you use a managed service or build it yourself to avoid vendor lock-in. The power architect maps these human decisions onto your technical setup. Azure landing zones are basically your org chart turned into code. The subscription a workload sits in defines an authority boundary. The management group structure shows how decisions flow from the top down. The RBAC roles you assign determine who can actually pull the trigger on a change. The technical structure must match the decision structure. When they don't, governance breaks. They turn these authority questions into technical guardrails. Who can deploy becomes a role assignment in a pipeline. What encryption is allowed becomes a policy that blocks bad configurations. How long does an exception last? Becomes an automated timer on a permission. Policy as code isn't just a theory, it is authority made executable. This role requires a skill most engineers never learn: organizational psychology. Teams don't bypass controls because they're being difficult. They do it because the control is too slow or it gets in the way of their actual job. The power architect doesn't just scream for more rules, they redesign the system so that being fast and being compliant are the same thing. If a deployment needs 3 signatures, people will find a way around it. But if the system auto-approves low-risk changes and only flags the dangerous ones, people will actually use the process. This takes a level of change management that most cloud experts lack. You can draw a perfect model on a whiteboard, but moving a real company with deep-rooted habits is a different story. The power architect knows how to phase a rollout and when to push for consensus. They realize that every technical change is actually a human change in disguise. The best architects treat infrastructure as a mirror of the organization. They don't just ask how to secure the cloud. They ask how the organization makes decisions and if the tools are helping or hurting that process. A startup needs speed, while a massive enterprise needs an audit trail. Those aren't technical specs, they are organizational requirements. This isn't just a new job title, it's a shift in how we think about what governance actually does. The operational compliance model, continuous over periodic. Moving from old school audits to continuous validation changes everything about how you stay compliant. For a long time, companies treated compliance like a scheduled event. Annual audits, quarterly reviews. A compliance officer checked a box every few months and then everyone went back to work. The assumption was that if we were compliant on Tuesday, we'd probably stay that way until the next check. But in reality, it does the opposite. Work changes every single day. Configurations drift in the weeks between audits. A security rule gets loosened or an exemption expires, and nobody notices because nobody is looking. Continuous operational compliance flips that model on its head. The question isn't, are we compliant? The question is, are we compliant right now? Not right now on a calendar, right now this second and the next second. And every moment the system is running. This requires a completely different way of thinking. You need Azure policy running evaluations in real time, not on a timer. When someone creates a resource, the policy checks it against the baseline immediately. If it breaks a rule, the system flags it or blocks it right then and there. You have Defender for Cloud watching the live environment and activity logs feeding into detection systems. The model is simple. Define the baseline, deploy policies to enforce it, monitor for drift, fix what you can automatically, and send the hard stuff to a human. It all starts with that baseline. What does compliant actually look like for you? You can't just say databases must be encrypted. That's too vague for a computer to understand. The policy needs to know the specific algorithm, how the keys are managed, and how often they rotate. Restricted traffic has to turn into specific protocols, CIDR blocks, and port numbers. These baselines have to stay fresh. Azure adds new features and security threats change every week. What worked last year is probably outdated today, and this is where most companies fail. They set up their policies, they deploy them, and then they never touch them again. The baseline gets stale and the environment drifts because the rules didn't keep up with reality. Exceptions need their own set of rules too. Sometimes you actually need to break a rule for a business reason or an emergency, but you have to track it. Who approved it? When does it expire? Why did we do it? The danger is when a temporary fix becomes permanent because someone forgot to turn it off. You have to treat exceptions as official parts of the system, not just messy workarounds. Your governance dashboard should show you the truth in real time. How many resources are out of sync right now? How many exceptions have expired? Who has too much power in their account? These aren't just numbers for a report. They are the signals that tell you if your governance is actually working. This shift requires a real change in culture. Teams have to accept that compliance isn't a one-time hurdle to jump over. It's a daily habit. The payoff for doing this is huge. You catch problems in minutes instead of months. You stop violations before they become a disaster. And you shrink the gap between what you think you have and what is actually running. This only works if your infrastructure is defined as code. And that is exactly why infrastructure as code is no longer optional. Why IAC is non-negotiable in an AI-native enterprise. The truth is counterintuitive. As AI agents get better at generating and changing your infrastructure, infrastructure as code actually becomes more critical, not less. Most organizations assume the opposite. They think that if AI can write the code, they can stop worrying about the discipline of IAC. They imagine the tool will handle the details, giving them more speed with less friction. That thinking is backwards. It ignores what actually happens when you put autonomous systems into a governed environment. When humans write code, your governance can afford to be a little loose. A human engineer carries context in their head. They understand the standards of the organization, they know where the lines are drawn, and they make judgment calls. If they deviate from a rule, they usually have a reason they can explain. That human judgment is a shadow governance layer. And it operates right beneath your formal policies. But when AI agents generate code, that judgment layer disappears. The agent doesn't know your company. It doesn't have context. It doesn't understand why your specific standards exist in the first place. It just follows statistical patterns. If its training data includes permissive configurations, it will generate permissive configurations. If the data shows hard-coded values, it will hard-code them. The agent doesn't have judgment. It has patterns. This is exactly why IAC is non-negotiable. IAC provides the deterministic layer that AI cannot provide on its own. It is the control plane where governance actually happens. When an agent generates infrastructure code, that output is just text. It might be correct, or it might be insecure and violate every policy you have. Without a governance layer, you simply don't know. With IAC as your control plane, you do. The model is explicit. AI agents generate intent, IAC captures that intent. Policy validates it. And then your CI/CD pipeline applies only what passes that validation. This chain only works if IAC is the single source of truth for what you deploy. If you start accepting direct API calls from agents or let them modify resources through portal APIs, you've broken the chain. You've created multiple sources of truth, and that is where governance fails. When infrastructure is code, versioning becomes possible. You can see who changed what and when, which makes your Git history a perfect audit trail. If an agent-generated change causes a problem, you can revert it instantly. You can compare versions to see exactly what is different. You aren't trusting the agent, you're auditing what it produced. Testing also becomes possible. You can write tests to validate code before it ever touches your environment. You can check if a template meets your security baseline, uses the right encryption, or follows your naming standards. These tests catch mistakes before they reach production. Without them, you're just hoping the agent got it right. Rolling back becomes a one-command fix. If a deployment goes wrong, you just return to the previous version for an instant recovery. Without ESC, if an agent modifies a cloud resource directly, you have to find the change and fix it manually. It's fragile. Without IAC, agent-driven changes are invisible to your audit systems. You won't have a record of the code, so you won't be able to prove the change went through policy validation. You won't even be able to answer the simplest question: is this resource compliant? IAC is the foundation for compliance when AI is involved. auditors can read code. They can verify that your controls were implemented and trace every decision through the policy layer. The future isn't AI replacing engineers, it's AI amplifying engineers while IRC keeps the governance intact. Organizations that build this discipline now, with clean code and rigorous testing, are the ones who will safely scale later. They've built the foundation. When agents join the team, the governance model keeps up. When the agent fails, the control plane catches it. If you skip this discipline, you're betting you won't need it. And that is how you build catastrophic risk. The future state, infrastructure as intent. The trajectory is unmistakable. Infrastructure is moving beyond code. This isn't just a prediction. Early adopters are already operating this way on their newest platforms and greenfield projects. They are moving toward a model where engineers stop writing code and start writing intent. In this world, the AI synthesizes the implementation. Policy validates the alignment. The human governs the constraints rather than authoring the templates. Today, the workflow is familiar. An engineer thinks about what they need and writes Bicep or Terraform to declare that state. They push it through a review, it passes policy, and CI/CD applies it. The code is the artifact. The code is the source of truth. Tomorrow, that workflow inverts. The engineer starts with the outcome they want. Maybe it's a highly available app serving customers across 3 regions, or a data pipeline that handles terabytes in real time. They describe this intent in natural language using a chatbot or a structured form. The mechanism doesn't matter. The intent does. An AI agent takes that description and synthesizes a complete blueprint. It might be Bicep, Terraform, or CloudFormation. The specific language is irrelevant. The agent generates the code to implement the intent, but it doesn't deploy it yet. Instead, the code flows through your governance pipeline. Policy as code engines check it against your organizational constraints. They look at security baselines, cost controls, and architectural standards. The policies validate the synthesis, so a human doesn't have to review every single line. The human approves the work at the intent level, not the code level. This requires a fundamental shift in how you think about your role. The mental model changes. You stop asking how to write a template and start asking what outcome you actually want. That distinction matters more than it seems. When your job is writing code, you focus on syntax and structure. When your job is describing intent, you focus on business requirements and what success looks like for the customer. The AI agent is just the intermediary. It translates your outcome into executable code. But translation is never neutral. The agent makes hundreds of tiny decisions while it works. It chooses which services to use, how to configure them, and what logging to enable. Those decisions reflect your organization's technical preferences and risk tolerance. The agent needs guidance through all of that. The underlying governance model doesn't actually change. Policy still validates, version control still tracks, and CI/CD still applies the changes. But because the human's role in writing the code vanishes, what you control has to shift. When humans write code, they use their judgment to catch subtle issues. That shadow governance layer is gone now. Since the AI agent only has patterns, your governance has to be explicit. It has to be airtight. Every constraint a human used to catch in a review must now be encoded as a policy. Every standard your team followed by common sense must now be enforced through automation. This is why you must define intent precisely. Vague intent leads to vague code. If you tell an agent to build a secure app, it means nothing. The agent will just make 1,000 guesses about what secure means to you. But if you ask for an application with AES 256 encryption, TLS 1.3, and managed identity authentication, that is precise. The agent can synthesize code that fits that exact specification. Your policy layer has to be just as sharp. You can't just say use best practices. You have to define which ones. You can't just say save money. You have to specify which SKUs are allowed and which regions can host your workloads. When policies are vague, the agent's output is vague. When policies are precise, governance actually works. The shift is moving from how do we build it to how do we govern the intent. That isn't just a new tool, it's a completely different discipline. The lessons from ARM to Bicep, what we know about successful transitions. The shift from ARM to Bicep teaches you something fundamental about how technology actually gets adopted. It goes way beyond just comparing JSON to a domain-specific language. Lesson 1 is almost obvious when you look back at it. Cognitive friction is real. It matters more than technical superiority. Teams didn't stay with ARM JSON because it was a better tool. They stayed because the cost of switching was high and the inertia of what they already knew felt comfortable. But something interesting happens when you introduce a tool that feels dramatically easier to use. Developers start opting in. They don't do it because management sends out a mandate. They do it because the friction disappears. When writing Bicep feels natural and writing ARM JSON feels like wrestling with syntax, people naturally gravitate toward Bicep. This has nothing to do with feature parity. It has everything to do with how much mental energy the tool demands from the person using it. If you remove the friction, adoption accelerates. This lesson extends far beyond infrastructure tools. Any technical migration that ignores human friction will struggle, no matter how perfect the replacement looks on paper. Lesson 2 is about the stickiness of legacy decisions. Switching costs are brutal. An organization with 300 ARM templates and established pipelines isn't going to migrate just for an incremental improvement. Rewriting those templates, retraining the teams, and rebuilding the pipelines is a multi-quarter project that delivers zero new business value. So, organizations stick. They maintain what works. They only invest in the new tool when business drivers finally force a change. It's not because the new tool is better, it's because the cost of staying put finally exceeds the cost of switching. Understanding this changes how you approach adoption. You don't try to convince legacy teams to move. You make the new tool the default for new projects and let the old code age out naturally. You watch adoption happen through attrition, not by mandate. Lesson 3 is about greenfield projects as the real drivers of change. When you're starting fresh, you default to the modern tool. Teams building new services don't carry the burden of legacy decisions, so they pick the tool that makes them most productive. This is where the real adoption happens. It doesn't happen in migration projects where switching costs paralyze every decision. It happens in new work where there's no legacy to defend. This should change where you invest your time. If you want to increase Bicep adoption, you standardize it for new projects and train new teams on Bicep instead of ARM. You let the older teams maintain their existing code. Within 3 to 5 years, the entire infrastructure portfolio shifts because new work accumulates in the modern tool. Lesson 4 shows us that governance has to be built into the tools, not bolted on afterward. Bicep's readability and modularity make code reviews possible. Policy enforcement feels natural. Security scanning actually works because the code is easy to understand. Compare that to trying to enforce those same standards on ARM JSON. The verbosity makes reviews painful and the modules are awkward to handle. The tool itself fights governance rather than helping it. This teaches a critical principle. Governance is a property of how tools are designed. When you're evaluating tools, don't just ask if they support policies. Ask if their structure makes governance easier or harder for the people using them. Lesson 5 is organizational. The shift from ARM to Bicep reflects a deeper move from infrastructure as configuration to infrastructure as code. That's not a technical change, it's a governance change. It means the responsibility shifts. You have to ask who owns the infrastructure and who is allowed to change it. The tool you pick embodies the answers to those questions. Picking a tool isn't just about picking a syntax, you're picking an organizational model. Lesson 6 is the most important. Change management matters more than the technology itself. The best tool in the world will fail if the organization isn't ready for it. If teams lack training and processes haven't adapted, the tool won't save you. The tool is just the mechanism. The organization has to be ready to use it differently. These lessons apply directly to what's coming next. The shift from IRC to infrastructure as intent will follow this exact same pattern. Cognitive friction will determine who adopts it. Legacy systems will persist because of inertia. Greenfield projects will drive the transition. Governance must be embedded in the tooling. And organizational readiness will determine your success far more than technical capability. Organizations that learned these lessons from ARM to Bicep are positioned to lead the next transition smoothly. Those that didn't will navigate it clumsily while trying to retrofit governance onto systems that weren't designed for it. So, what should you actually do right now? The immediate actions, what leaders should do today. The theory is clear and the direction is unmistakable, but clarity doesn't solve the immediate problem. You have infrastructure code, you have teams, and you have processes built around specific tools. You need to move in the right direction without paralyzing the business. Start with your tool inventory. If ARM templates are your foundation, don't announce a massive migration. Instead, make a deliberate choice that all new projects will evaluate Bicep. Existing templates stay in ARM until they require significant changes. When a team needs to rewrite a template for new functionality, they rebuild it in Bicep. This approach eliminates the switching cost trap. You're not forcing a rewrite that delivers no business value. You're letting modern tooling become the default for forward momentum. Over 18 months, your portfolio naturally shifts through accumulated choices rather than mandates. If Terraform is your current standard, you need to ask a harder question. Do you genuinely operate in multiple clouds? Or are you paying a multi-cloud tax for single cloud infrastructure? Many organizations standardize on Terraform for consistency across AWS, GCP, and Azure, but then they discover that 85% of their workloads run exclusively in Azure. The unified model sounds ideal until you measure the actual operational overhead. You have to deal with state management, provider version dependencies, and the mental load of maintaining abstractions for 3 clouds when you're only using 1. If you're predominantly on Azure, the calculus changes. Azure native services offer tighter governance and simpler operational models. You might be better served by using Bicep for your core infrastructure and keeping Terraform only for the outlier cross-cloud components. Next, implement continuous drift detection immediately. This doesn't require any tool changes. Azure policy runs on your existing infrastructure, and Defender for Cloud scans it continuously. You can integrate IAC scanning tools into your pipelines right now without waiting for a total transformation. Start surfacing the gap between your intended state and the actual state. Start seeing the drift that's currently invisible to you. This creates the visibility that drives everything else. Once leadership sees the scope of configuration drift, the urgency for governance shifts from an abstract idea to a concrete problem. Codify your governance into policy as code. Write Azure policy definitions that express your compliance requirements, security baselines, and cost controls. These shouldn't be documents that people read once and forget. They need to be executable rules that the system enforces. Start with your most critical constraints, the ones that create the biggest risk if they're violated. Deploy those policies and let the system catch the violations. You can build the rest from there. Establish a governance ownership function. You can call it a power architect or a governance engineer. The title doesn't really matter. What matters is that someone owns the authority structure. This person maps decision rights onto your technical architecture and ensures the governance system reflects how your organization actually makes decisions. This is a strategic architectural role, not just an individual contributor task. It shapes how your entire infrastructure organization operates. Invest in team training around ISC discipline. Code reviews, version control, and CI/CD pipelines aren't optional niceties. They are the foundation that everything else depends on. Teams that are fluent in Git and comfortable with code reviews can adopt new tools rapidly. Teams that skip this foundation will struggle with any ISC tool, no matter how modern it is. Start piloting AI-assisted code generation in non-production environments. Keep it in the sandbox for now. Let teams generate templates so they can understand where agents excel and where they fail. You need to build familiarity and develop guardrails before agents touch anything that actually matters. Implement controls around agent access right from the start. Use least privilege credentials and policy validation for agent outputs. You need comprehensive logging of every action an agent takes. These aren't restrictions you add later. You build them into the initial pilot. Make guardrails the default assumption. Build observability into your infrastructure now, because you can't govern what you can't see. Invest in dashboards that surface resource health, configuration compliance, and cost allocation. These are foundational investments that enable everything else to work. Finally, begin planning for the shift from IAC to infrastructure as intent. Understand which policies will need to be comprehensive and how authority structures will shift. Think about the team skills you'll need. This isn't a project you start tomorrow morning, but it is a transformation you should be preparing for today. The risk of doing nothing. Why delay is costly. Organizations that resist modernizing their infrastructure don't face a future where everything stays the same. They face a future where the gaps widen. Configuration drift won't solve itself. Without ISC discipline and continuous governance, the problem doesn't plateau. It accelerates. As your cloud environment grows, as teams multiply, as deployment frequency increases, the gap between your intended state and the actual state expands faster than any manual review process can handle. You're not managing drift, you're drowning in it. Security incidents driven by drift don't decrease because you ignored the warnings. They increase because the surface area grew while your controls stayed static. Manual governance stops working at scale. At a certain size, checklists become useless. Spreadsheets tracking exceptions get out of sync. Manual reviews bottleneck every change. Organizations at that scale make a choice. Either invest in automated governance or accept that governance stops functioning. Teams that accept the second option don't get faster, they get chaotic. Changes start bypassing approval processes. Security reviews become rubber stamps. Exceptions become permanent because nobody tracks them anymore. The organization loses the ability to answer basic questions about its own infrastructure. Compliance costs escalate when you're not continuously managing posture. A quarterly audit discovers that your configuration has drifted from your compliance baseline. Remediation requires weeks of effort. Your organization pays penalties. Next year, the same thing happens because nothing fundamentally changed. You're not building continuous validation, you're just building a repair cycle. And each cycle costs more than the last because the scope of the problem grows. The talent gap widens in organizations that cling to legacy practices. New engineers expect modern infrastructure tools. They expect to work with code, not portals. They expect CI/CD pipelines, not approval committees. When they join a team still doing manual infrastructure work, they're shocked. Many leave. The ones that stay become frustrated. The organization develops a reputation. You become the place where infrastructure is done the old way. Recruiting becomes harder. Retention gets worse. The team responsible for your most critical systems is slowly hollowing out because you didn't invest in modernization. When AI agents become mainstream, organizations without strong IAC discipline face governance chaos. Agents will exist. Your competitors will be using them to generate infrastructure code in minutes instead of days. If your organization hasn't built rigorous ISC discipline, if you don't have policy as code in place, if your CI/CD pipelines aren't designed to validate automatically, then agents touching your infrastructure become a security nightmare. An agent generates insecure code. It gets applied. It stays applied until someone notices. That's a breach waiting to happen. Organizations that skipped ISC investment will be scrambling to build governance after the damage is done, trying to retrofit controls onto systems that weren't designed for them. The competitive disadvantage is concrete. Organizations that move infrastructure changes in hours while you're moving them in weeks are outpacing you. They're experimenting, iterating, scaling. You re-bogged down in process friction. That's not just a speed problem, that's a strategy problem. You can't move as fast as the market demands. Competitors beat you to new capabilities. Your cloud cost explodes because you can't optimize infrastructure as quickly as cloud pricing changes. Your security posture lags because you can't respond to threats as fast as they emerge. Security posture degrades silently in the absence of continuous governance. Drift accumulates invisibly. Exceptions become permanent without being noticed. An engineer opens a security group for debugging and forgets to close it. A temporary policy exemption becomes part of the baseline. A logging configuration gets disabled and never re-enabled. Each individual change is small enough that nobody notices. Collectively, they erode your security surface. Then a security audit surfaces the damage. Or worse, an attacker finds the exposed surface before you do. The cost of remediation grows exponentially. Fixing drift in a small environment is manageable. Fixing drift in a large, complex estate is a multi-month project that pulls engineers from productive work. The larger your environment, the worse the problem becomes. A year of accumulated drift in a 500 resource deployment is expensive to unwind. 3 years of accumulated drift is a crisis. You're not just cleaning up configuration. You're rebuilding governance from scratch while running production workloads on broken foundations. The organizational credibility of your infrastructure team erodes when governance fails visibly, when deployments fail repeatedly, when drift causes outages, when compliance audits find violations the organization didn't know existed. Leadership loses confidence. Budget requests get rejected. Hiring freezes happen. The team becomes seen as a blocker rather than an enabler. Recovery takes years. There's a path forward, but it requires starting now. The model behind modern infrastructure, understanding the shift. Everything hinges on where you store the source of truth. That's the real distinction between the three infrastructure models, not the tools, not the technology stack. But the fundamental question, when something about your infrastructure matters, where do you look to find the answer? The oldest model treated the running environment as the source of truth. Infrastructure as configuration, a series of manual steps, documented in runbooks and tribal knowledge. Someone built the network, someone else deployed the application servers, another person configured the load balancer. Each person carried knowledge in their head. The documentation lived in wikis that got out of sync the moment the environment changed. If you wanted to know what the infrastructure actually looked like, you logged into the portal and looked. The running system was the only reliable source, the only place where the truth lived. This model worked when infrastructure was simple, when teams were small, when change was infrequent. The moment complexity grew, the moment teams scaled, the moment change accelerated, this model broke. You couldn't document fast enough. Knowledge couldn't transfer fast enough. The moment a key person left, their understanding of the infrastructure left with them. If something went wrong, you were debugging by trial and error because nobody had a definitive record of how it was built. The next shift moved the source of truth to code. Infrastructure as code. Version-controlled files that declared desired state, reviewed like application code, deployed through CI/CD pipelines. Git became the single source of truth. If you wanted to know what the infrastructure looked like, you read the code, not the running environment, the code. The difference is profound. Code can be reviewed before it's deployed. Code can be tested. Code can be rolled back. Code creates an audit trail. Code enables reproducibility. But this model requires a different skill set. Teams that had been clicking portals suddenly needed to understand version control. They needed to write code. They needed to think about desired state, not sequences of steps. They needed new tools, new processes, new cultural norms. The shift from configuration to code was traumatic for many organizations because it demanded not just a tool change, but a fundamental rethinking of how infrastructure work happened. The model now emerging moves the source of truth one level up. Infrastructure as intent. The code still exists. The code still matters. But the source of truth isn't the code anymore. It's the policy and constraints that govern what code is allowed. It's the intent that the code is meant to express. If you want to know what the infrastructure should be, you read the policy layer. You understand the business requirements and security constraints. You read the intent description. The code is the implementation detail that the system generates and manages. This creates yet another shift in skill sets and organizational structure. Teams don't write code anymore. They write policies. They describe intent. They govern constraints. Code authoring becomes something agents and automated systems do, not something humans spend their time on. The infrastructure engineer's role transforms from coding to governance design, from implementation to intent articulation. Each shift represents a real transformation in who holds responsibility. In the configuration model, responsibility is diffuse. Whoever made the last manual change owns that piece of the infrastructure, but there's no accountability because changes aren't tracked. Responsibility is tribal. In the code model, responsibility is explicit. Someone wrote this code. They're accountable for it. Code review means someone else verified it before deployment. Responsibility is clear. In the intent model, responsibility inverts. The intent owner is accountable for the outcome. The agent that synthesized code is not accountable. It's executing within guardrails. The policy designer is accountable for the constraints. Responsibility becomes structural rather than individual. The shift from configuration to code was traumatic. The shift from code to intent will be equally challenging. But organizations that understand which model they're operating in can anticipate what comes next and prepare for it accordingly. That understanding shapes everything else. The convergence, IAC, governance, and AI coming together. You're at a convergence point. It is not a choice between three separate technologies. It is three interconnected trends, and they only work when they function together. Infrastructure as code provides your foundation. The deterministic layer, the versioned artifact that governance can actually operate on. Without it, you have no source of truth, no reproducibility, no control plane. IAC is the mechanism that makes everything else possible. But IAC alone is not enough, because code without governance is just faster chaos. You can generate insecure infrastructure more rapidly without meaningful controls. You can deploy policy violations to production in seconds instead of days. Speed without constraint is a liability, not an advantage. That is where the governance layer becomes essential. Governance provides the constraints. The policy as code framework that evaluates whether code aligns with what the organization needs. It is the continuous monitoring that surfaces violations, the automated remediation that corrects drift, the authority structures that ensure decisions flow through the right channels. Governance turns ISC from a tool into a controlled system. But governance has limits. The human-driven parts do not scale. You can write full policies, but maintaining them requires constant attention. You can design authority structures, but keeping them aligned with reality requires ongoing adjustment. You can perform code reviews, but the cognitive load of reviewing thousands of deployments is unsustainable. That is where AI agents create leverage. AI agents amplify what is possible within the governance model. They generate code at scale. They analyze vast amounts of telemetry. They coordinate workflows across services. They do what humans cannot do efficiently. They process volume. But agents are only useful when they operate within constraints. Without governance guardrails, agents become a risk vector, not a productivity tool. The convergence is this. IAC creates the control plane. Governance defines the constraints. AI agents operate within those constraints. This amplifies human capability without removing human control. Organizations that thrive in the next 5 years are the ones that understand this is not a technology choice. It is an operating model. You are not choosing between IAC, governance, or AI. You are designing a system where all three function together as a single whole. Think about what this means operationally. An engineer describes what they want the infrastructure to do. A natural language interface captures that description. An AI agent generates code in your standardized language, like Bicep, Terraform, or CloudFormation. The code flows immediately to a policy engine. Does it meet your security baseline, your cost controls, your architectural standards? The policies validate without human intervention for routine deployments. Complex or high-risk changes escalate for human review, but the human is not reviewing raw code. They are reviewing a diff, a summary, an impact analysis. The agent synthesized all the details, and the human governs the outcome. If the policy check passes, the code goes to CI/CD, standard deployment pipeline, version control, audit trail. The deployment happens. Continuous monitoring runs. Real-time drift detection compares the actual state to the desired state. If a deviation occurs, the system detects it immediately. It flags it to the governance team. For low-risk deviations, it remediates itself. For high-risk changes, it escalates. Everything is logged. Everything is auditable. Everything is traceable back to the original intent. This operating model only works if all three components function. Remove ISC, and you lose the control plane. Governance and agents operating without a deterministic artifact is chaos. Remove governance, and ISC becomes a faster way to deploy insecure infrastructure. Agents generate code without constraint. Remove agents, and your governance team is manually reviewing thousands of changes every month. The human labor becomes the bottleneck. The shift from ARM to Bicep is a preview of this larger system. It shows that the industry can evolve its tooling when the model demands evolution. It demonstrates that cognitive friction matters. Tools that are hard to use do not scale, no matter how technically capable they are. It proves that governance is more effective when it is embedded in tooling rather than bolted on afterward. Bicep's readability enables policy enforcement. Its modularity enables code review. Its structure enables governance. The lessons from that transition apply directly to what is coming. Organizations that learned them are positioned to lead. Those that did not will be playing catch-up. They will try to retrofit governance onto systems that were not designed for it. They will try to control agents that operate without meaningful constraints. They will try to scale manually when automation should be handling the load. The time to prepare is not when agents are mainstream. It is now, when you can still build the foundation methodically, when you can establish IAC discipline without rushing, when you can design governance systems thoughtfully, when you can pilot agent integration carefully. The organizations that do this work now will not be scrambling to catch up later. The future is already here, it's just not evenly distributed. The shift from manual infrastructure to code to intent is not a prediction. Early adopter organizations are already operating this way. The question is not whether this shift will happen. It is whether your organization will lead it or follow it. ARM templates were a mistake. Not because the technology was bad, but because they revealed something fundamental. The tools we use shape how we think about problems. Bicep won because it aligned the tool with how humans actually think about infrastructure. The next tool will win for the same reason. It will align with how we think about intent and governance. Your infrastructure strategy today determines whether you are leading or following that transition. The choice is yours.